Today we're going to learn some rules that will make our analysis of op-amp circuits significantly easier. So these are called the op-amp golden rules. And these only work for op-amps that have negative feedback. So that is, they have a path connecting the output to the inverting input, and that's typically a resistor between those two. If an op-amp circuit does not have negative feedback, we have to solve it with techniques like we've done before, kind of more step-by-step, more thinking, I guess. So here are the op-amp golden rules. All right, here are our op-amp golden rules for a circuit with negative feedback. So the first is our op-amp will do whatever it can to make V plus minus V minus equal to 0. So just a reminder, our op-amp has two different inputs, the inverting input and the non-inverting input. And so if it has negative feedback, that is a path connecting the output to the inverting input. As shown here, it's going to do whatever it can to make these two inputs, this input and this input, the same voltage, or have them have a difference in voltage of 0, which means they are the same. Our second golden rule is that the inputs, the inverting and non-inverting inputs, draw 0 current. So no current enters the inverting input or leaves the inverting input, and the same for the non-inverting input. All right, we'll deal with this one just because I have more room below it right now. So what this means practically is if we have a path, if we have things connected to our inverting input and then things going past it, this means that often it's really easy to look at things in terms of voltage dividers, because remember, voltage dividers only work for components in series, where it doesn't work for things not in series because there's current that can leak out between the two objects. So if we have something like this, I guess let me draw a bigger example. If we have something like this, where we're looking at some voltage here and some voltage here, week 1 of 315 analysis would say, oh, well, we can't treat these two as a voltage divider because there's something connected in between them, right? So we're not allowed to do that. But what this golden rule is saying, our inputs are drawing 0 current, which means there is no current entering or leaving the resistor circuit at this point. This is just a voltage measurement, basically. And so that means that we can treat this as a voltage divider sort of setup. So that makes solving some problems much easier. Easy to identify voltage dividers because of that. All right, now let's go back to the first rule. So the op-amp will do whatever it can to make the difference between the two inputs equal to 0. Now, can is kind of the important word here. Our op-amp is limited in its capabilities. So an ideal op-amp can make its output supply as much current as needed, or can be at any voltage. In real life, we're limited by the power supplied to our op-amps. So what we're going to say are our rules for what it can do here is we're going to use numbers for an op amp that we often use in lab, a 741 op amp. We're actually not using these in lab this semester because of our equipment changes. So what we're going to put as limits on our op amp are the output has to be between plus and minus 15 volts. So these would be, the power that we're supplying to this op amp from whatever our external power supply is. And the current at the output is limited to being less than 25 milliamps. And again, both of these are going to depend on the actual model of op amp you're using and to some degree how it's set up in the circuit. But for solving problems on the board, we're gonna take these as example numbers to use. And if we're doing things in lab with different numbers, I'll tell you, or if you're building things on your own with op amps, these are things that you should be aware of when you're designing or building circuits. So like I said, so these numbers are roughly based on 741 op amps, which we are not using, but we would use if we were in person. Okay, great. So with these golden rules, I want to go back and analyze our op amp circuit from the last video and just show you how easy it is to figure out what's going on with these rules. So our circuit from last week looked like this. We had an op amp with the non-inverting input grounded. The input voltage to the circuit went through a resistor to the inverting input, and then there was a feedback resistor between the output and this inverting input. So this is our output voltage. We had values for these resistors. This was 1K, this was 10K. And now let's do a little analysis. So what we would like ultimately is what V out is in terms of what's going on over here. So that's going to be our input voltage and potentially these two resistor values. Okay, so our op amp golden rules are the following. Remember, so the op amp is going to try to keep these two voltages the same. So that is, this is V minus and this is V plus. So we want V minus equal to V plus, and that we actually know because V plus is grounded, so that is equal to 0. So our op amp is our first rule is telling us that our op amp is going to try to keep this point at V equals 0 because this point is at V equals 0. Okay, so that's rule number 1. The second rule is that we don't have any current in or out of our two inputs. So for V plus, that doesn't really matter because nothing interesting is happening here. This is just grounded. But for this does matter, and I'm gonna erase stuff around this here. So why this matters is if we look at just this circuit, V in, resistor, resistor, V out, now we have an attachment at this point between these two components, right? And as I mentioned when I talked about the golden rules a moment ago, if we just had something that looks like this and this went over to some other unknown component, we would not necessarily be able to use the voltage divider equation for this because the voltage divider equation only works for things in series with nothing connected between them. However, the golden rule is telling us that the current equals 0 in this part of the wire. So if the current equals 0 here, then we could think about this two ways. One, in terms of how the current flows, that's no different than if nothing was connected there at all. So that's kind of the answer right there. The other piece, I guess, is that to derive the voltage divider equation, what we did is we found the current in this whole thing and then said, oh, okay, well, V equals IR. So the current drop you get for each of these things is that current times whatever this resistance is. Now, that doesn't work if they both don't have the same current. But we here have shown that they do have the same current because there is no current exiting or leaving at this point because of the golden rule. And so the current through this has to equal the current through this, which means our voltage divider equation does work. Okay, so anyway, that lets us do the analysis of a circuit that just looks like this and ignore whatever wire is attached there because we know there's no current. Okay, so this is what we now have to analyze. And in addition, we know one other piece of information from our first rule, and that is that this point here equals 0. So I will erase this just to make some room. So our analysis looks like this. We have this current that is equal to this current, right? This current is equal to this voltage difference over R. So that's Vin minus 0 over 1K. That is our current. And that has to equal this current. That's the same thing, but we could write this as 0 minus V out over the 10K. Okay, so like I said, we wanted to solve for V out in terms of V in. So just solving this really quickly, we have V in over 1K equals minus V out over 10K. So solving for V out, I get V out equals minus 10K over 1K times V in. So that is minus 10 V in. So our output is a factor of minus 10 times our input. So this is an amplifier with a gain of minus 10, also called the inverting amplifier. And that is what we called this circuit before. It is an op-amp inverting amplifier circuit. So, once we know these golden rules and understand how to use them, the only analysis we had to do to understand what's going on in this, new complicated-ish amplifier circuit is to solve this picture, which is very easy. This is like a week 1 electronics problem. So that's why the golden rules are so nice. They make solving these sorts of op-amp problems very, very simple.